Calculus 2, Section 4.7, Antiderivatives. First of all, a definition. And of course, first thing I do is move things out of the way. Just a moment. Okay. A definition. Sorry, that D is very terrible. A function capital F is an antiderivative of lowercase f on an interval called I if f prime of x, or the derivative of capital F of x, equals little f of x, for all, that's what that upside down A means, for all x elements, that's what that C with the line through the middle means, for all x elements of this interval I. Okay, so a function f is an antiderivative, so that's what the definition's for, of little f on an interval I if the derivative of capital F equals little f of x for every x in that interval I. So the antiderivative means that it's the thing you took the derivative of. So, this another definition here, so we can get these definitions out of the way. The process of recovering a function that's that capital F of x from its derivative that's that little f of x is called antidifferentiation. Antidifferentiation. That's the process. So, in general, we use capital letters to represent the antiderivative, and lowercase letters for the function that you would get once you took the derivative of the capital F. So, capital F antiderivative, little f regular function. The function, I guess. The derivative of the function. Let me write this down maybe another way. F is a function and capital F is the antiderivative. That's the function you took the derivative of to get the little f, if that makes sense. So what are some examples of this stuff? Let's go to new screen. So if f of x is 1/2 x squared, what did we take the derivative of to get 1/2 x squared? What is the capital F of x, the antiderivative? Well, if you think sort of backwards, when you take the derivative of something like this is just a polynomial. You take the exponent and multiply by the exponent and then subtract 1 from the exponent. So, we know x is what it's got to be. Let me start with f of x here. We know we got to have an x because that's the variable. Now, the x before must have been a 3 because I subtracted 1 from it. And I would have taken a 3 and multiplied out front, but I don't have a 3 out front. So somehow I had to cancel the 3. So there had to be, and I'm going to put it to the right, so there had to be a 1/3 out here, right? Because if I take the derivative of this, I would have to multiply by 3. That would get rid of the 3. But I do have a 1/2. Where did that come from? It must have already been there. So x is the variable. I had degree 1 more than the 2. There's no 3, so I must have been able to cancel the 3's, but there was a 1/2 there. So this came from really 1/6 x cubed. And of course, how do you check that? You take the derivative. So this is sort of nice. Remember how you used to check? So let's see, the derivative. See, that's right. I multiply, so it's 3 times the 1/6 times the x, subtract 1, and 3 times 1/6 is 3/6 x squared, or 1/2 x squared. So this is the function little f, and big F must have been this. Does that make sense? Now you can start guessing and then check by taking the derivative. That's some good practice. That's why we went through that derivative worksheet. Because this is sort of like when you did division for the first time. You were asking, what did I multiply to get this number? Sort of looking at the opposite. So let's see here. We have another one. We're going to use a little g. And we're going to say that is sine x. So what is the capital G of x? It's antiderivative. Well, let's see. What do I take the derivative of to get sine? Well, I take the derivative of cosine. But hold it just a second. When I take the derivative of cosine, it's not just sine, it's a negative sign. But I don't have a negative. So I must have had a negative here to cancel the negative once I got to the little g. Does that make sense? Another way to look at that is you can always put the negative there and then say with cosine, I guess, if you looked at it this way, or sine. If this is what I needed, if that's what you're thinking, because the derivative of cosine is a negative sign, but I needed that negative to get it out of there. Doesn't really matter, I guess. You need to come up with your method of figuring these things out. Some people it's so easy. For some, myself included, these are a little bit confusing. Now, what we want to also mention here is that up above, that capital F of x equals 1/6 x cubed is not the only function that would work. Let's use a subscript here. So that one of the functions that would work. Can you think of another function that would work that would give you the same answer, this 1/2 x squared? Well, the easiest way to do that is saying, well, if I added a constant, then the derivative of constant is 0, and it would be the same. And you could say that means that there's really an infinite number of these, because I could add a bunch of different numbers. An infinite number of numbers. So this, when you add that plus c, that constant, to the end, this is now the family of antiderivatives that you would get. And that way, you have the general derivative, or what we call, we'll talk about that, I guess, in a moment. We'll give that a name in a second. So, what is this c, and how do we know what c is exactly? We would need some extra information. To find c, to find out what exactly that would be. They would have to give us some information for us to plug in and essentially solve for c. How do they do that? Well, let's take a look at this on the next screen. So we've got f of x, which is, f prime of x, which is little f of x, which is the 1/2 x squared. That was really the original problem. We wanted to find f of x, and we wanted to find it for the precise function, not with the plus c, but the exact function. So, if you also know that capital F of 1 equals a -1, then you can plug that into the capital F and find out what c is. Because, remember, f of x is that 1/6 x cubed plus c. So now in order to plug this stuff in, then you say, okay, this f of 1, when x is 1, the function is a -1. So a -1 is 1/6 when you plug in a 1 for x plus c. Well, that means it doesn't matter whether you triple or take it to the 300th power. This is just 1/6. So -1 is 1/6 plus c. Subtract 1/6 from both sides. Well, that's a -6/6 and a -1/6. So c must be a -7/6. And now our function becomes 1/6 x cubed minus 7/6. And that gives you the exact antiderivative. It's what they call an initial value problem. So when they ask you for that, to solve this initial value problem, they must give you information so that you can come up with the exact antiderivative. On my LSMSA, you need to make sure that you've downloaded you've already done the worksheet, the derivative review, and probably taken these derivative rules already downloaded. Make sure you also get the integral formula sheet on my LSMSA. And that's going to be necessary, well, maybe not necessary, but helpful for solving some of these. So make sure you go to the downloads and get all the things, I guess, that you haven't gotten yet. That same place where you clicked on this video to watch it. So, these initial value problems are really the first differential equation problems. So when you take diff EQ, you really had a little bit of this already, because these equations contain derivatives, so they're called differential equations. And you're trying to find out where that equation came from exactly, with the constant and everything included. So, what are the steps you might follow for this? First, you find the antiderivative. And then you plug in the values the initial values to calculate C. Let's do another example. Suppose you're given that dv dt equals 8t plus cosecant squared t. You're also given that v of pi over 2 equals a negative 7. It's a 7. First of all, we got to find the antiderivative. What was v of t to begin with? Well, let's see. If you look at those integration rules, if it's a polynomial, it's one of the easier ones, just like the derivative. You take the exponent, add 1 to it, and then divide by that new exponent. So it's 8t, add 1, 2, divide by the 2. So polynomials, again, are going to be the easiest ones to find. What did you take the derivative of to get cosecant squared? Remember, that's that cotangent of t. But also remember that these cofunctions, their derivatives were the negative. So in order to get a positive, it must have been negative before. Does that make sense? Because this will give you a negative cosine squared, and with this negative, it'll be the positive cosecant squared. I'm sorry, did I say cosine? For the cotangent t, it is a negative cosecant squared t, but we have to make this a positive. And always pop in that plus c. Here we're saying that the function v is a negative 7. And let's do a little work here. This is 4t squared minus cotangent t plus c. But hold it, this is not t. This is pi over 2. So this pi over 2 gets plugged in. Pi over 2. Now this one is a t squared, so it's really pi over 2 squared. And the cotangent, we'll get to the cotangent in a second. So negative 7 equals, so this is a pi squared over 2 squared, which is 4, but you're multiplying by 4, so you just have pi squared left. Cotangent at pi over 2. Well, if we remember our trig, and that's why you take trig first, one of the reasons. At pi over 2, we're up here, which is the point 0, 1. The cotangent is x over y. So it's 0 over 1 plus c. So we're going to, this is a 0. We're just going to move the pi squared over the other side. So it's really, I guess both these are negative. Negative pi squared and a negative 7. I guess you could pull that out front. See if I can squeeze this answer in here. So v of t is 8t plus cosecant, I'm sorry, plus minus rather, gosh, and now I've gotten this all mixed up, is 4t squared minus cotangent t plus the constant And we could do a minus pi squared plus 7 in parentheses. Not real clean, but it works. And what this shows you, I guess, is you can certainly get 4 steps from this. And if you make a mistake, I guess that's why I suggest pencil and paper, so you can erase them. If you're doing with ink, because you really like ink the way it looks, you can scribble it out. Don't recopy this. I think I could read this even, since I did the same thing. Now we're going to talk about antiderivatives and motion. And this is sort of an interesting topic because it relates to physics. The acceleration due to gravity, if you're in the English system, is a negative 32 feet per second squared. Feet per second per second. The negative is because it's going down towards the center of the Earth. 32 feet every second per second. So this acceleration is pretty fast. I think it's negative 9.8 meters per second squared. We could have done that also. And I'm not sure, I think they use both, but perhaps meters more than the feet. I guess, the old school with the feet. Doesn't really matter. You could make this anything you want. In fact, we're going to talk about on a different planet sometimes for some of these problems. So, what's interesting is, you probably remember that the S of t is motion. This usually is S sub 0 plus v naught t plus 1/2 at squared. I don't know if you remember that. But if you take the derivative of this, ds dt, that is like, if this is feet, this would be feet per second. This is velocity, v of t. And if you take the derivative of this quadratic up here, a constant is 0. This v naught t just gives you v naught, the original velocity. And if we multiply by the 2, get rid of the 1/2, you just have at. So velocity is v naught plus at, acceleration times time. And if you take the second derivative of this motion or position with respect to t twice, you really get the derivative of velocity with respect to t, which is the derivative of this. V naught is a constant, so that's 0, and you just get a. So, if they give you a, the acceleration, no matter what planet you're on, you should be able to find the antiderivative to get the velocity, and take its antiderivative and get the position function. And that's what we're going to try to do with this. So, the antiderivative of this, if you think about it, velocity with respect to t. Now remember, if it's a constant, you just tack on a t and you can multiply by 1 if you want to. But it's really a negative 32t plus some constant. What is that constant? That's that original velocity. Now, at this point, you need that initial value problem information. So, if we wanted just the velocity, we'd need something like at t equals 0, v equals 0. So if we're given that information, we're going to plug that in. And v is 0 when t is 0 means c would also be 0, I guess. And you just get this negative 32t for v. But of course it could be something different. This means that at time 0, you're sitting still, no velocity. But you could have been falling or whatever. Does this make sense? If you take this and say, okay, what is the antiderivative here? Which now becomes the second derivative of s, which is the acceleration due to gravity. You can call it a of t, I guess, if you want. So you have to add 1 and then divide by the new one, which is t squared, add 1 to the exponent, divide by the new exponent. Or a negative 16t squared. You might have seen this in places. Plus some constant c. Well, they'd have to give you some information, not about v anymore, but about the acceleration. And if they give you that the acceleration is 0 when t is 0, meaning it's sitting still, then we can also plug that in. 0 equals a negative 16 0 squared plus c. So once again, c equals 0. And the acceleration is a negative 16t squared. Now these were at time 0, the velocity and acceleration are 0. Really makes sense. It's when it's called many times free fall, because you're holding a rock or something above the earth and you let go, and so the initial velocity is 0, its acceleration is 0, and the only thing acting on it is this acceleration due to gravity, and that controls the velocity and how soon you reach that negative 32 feet per second squared stuff. Sort of an interesting, if you would remember this, I think, then you might have a little easier time with physics. Because take the derivatives of these, or take the antiderivatives of these, you can go either way. And now finally we get to use this integral word with indefinite integrals. This is an E, by the way. Integrals. So, first of all, a definition. The collection of all antiderivatives of little f all antiderivatives of little f represents the indefinite integral. Of f, of f, WRT, let's do this down here. Of f, put the f here. WRT is a short thing mathematicians use because they're lazy. With respect to, so it's the indefinite integral of f with respect to x denoted. So, when you see this squirrely thing, f of x dx. So that little squiggly thing is the integral sign. If we need that when we're typing things in, we're going to use the tilde, which is sort of on its side. Hopefully we won't have to type those in too much. We're doing our tests online on my LSMSA. There's no really easy way to make sure everybody can do this cool S-looking thing. So we might use the tilde, and if we need limits of integration, we'll plug that in here. So just remember that, I guess. Tilde, is that how you spell it? Anyway, tilde. Anyway, doesn't really matter. Here is the function. It's called the integrand. That's the whole thing, really. And dx is the variable of integration. So I guess the integrand is just this portion. And the variable of integration, because you can have a function written in terms of x, but take it with respect to t, and we'll talk about that later. So, as an example, see if I can do this nice. 1/2 x squared dx. What this is asking is, I want to find all of the collection, the family of antiderivatives, where when I take the derivative, I get this. And if you'll remember, that is that 1/6 x cubed, and to get them all, you could always do plus c. So, don't forget that plus c. It's a nice way for a teacher to take a point off. Indefinite integrals. Put a plus c, because you want the whole family. Now, if we want to try a few examples, just a couple. Go to a new screen. What is this is number 30, I guess it is. The antiderivative, or the indefinite integral, of 1/7 minus 1 over y to the 5/4. Oh my gosh. That's the integrand. And dy is the variable of integration. We're doing this with respect to y. Good, because that's the variable here. So, what do you get first? Well, what you'll find is you can take sums and differences and do those individually, just like taking the derivative. The derivative of a difference is the difference of the derivatives, so we can essentially set these up as a indefinite integral of 1/7 with respect to y minus the indefinite integral of 1 over y to the 5/4 with respect to y. That's what that dy means, with respect to y. Now, the derivative, or the antiderivative of a constant, you just have to put that variable on there, 1/7 y. Because if you take the derivative of this, it's 1 times the 1/7, subtract, so you get just 1 here, and it's just the 1/7. The derivative of any, just with the variable, is just that coefficient. Now, I'm going to write this. I'm going to take a couple steps for this, since I need 4 steps anyway. Y to the negative 5/4 dy. And then I can think of that a little differently. So, what do I need to do for things like this? Well, remember, you add 1, so it's a negative 5/4, plus 1, which I'm going to write as 4/4, and then divide by the new negative 5/4 plus 4/4. And then, of course, plus c. Now, you might say, don't we have a different c for this first one and the second one? We can put the constants together, whatever numbers they are, add them up, and just make it one constant here. So, it's the 1/7 y. Now, let's take care of all these things. A negative 5/4 plus 4/4 is really a negative 1/4. And you can write it that way for right now. Negative 5/4 plus 4/4 is still a negative 1/4 plus some constant c. So 1/7 y. This should be plus because you have 1/4 in the denominator. It's 4. And this is y to the negative 1/4. You can put that over y to the 1/4 plus c. Several ways you could write this. Does that make sense? That is at least 4 steps. Let's do another one. How about number 38? Some of these look harder. That's one reason I chose this. It looked harder, but I think it's easier. Now, on my LSMSA, it's going to be hard to get these thetas and stuff, but they're going to give them to you in the text. 3 cosine 5 theta d theta. And what we'll have to assume, if they don't have parentheses around it, that this is parentheses. This whole thing is in the integrand, and this is the variable of integration. So, but this is multiplication, so let's see. What did I take the derivative of to get cosine? Well, I took sine. And of course I took the same 5 theta, because you just use the same argument. But then, chain rule said I had to take the derivative of this 5 theta, because that's the derivative of the variable of differentiation and integration here. So I needed a 5. But in order to get a 5, I needed a 1/5. Of course, I always had the 3 plus some constant c. So this is really 3/5 sine 5 theta plus some constant c. So this one was easier than the last one, which looked maybe easier. Maybe it didn't. I don't know. Trig functions sometimes look really hard. They can be really easy. Okay. Your assignment, page 241, 5 through 105, you can spread that over 2 days if this is the first day you've been looking at this video. If you got through part of it and started the problems, there's 20 of them, or 21, I guess. But, let's see, what did I think 105, I'm going to have to take off there. Yeah. So, if it still says 105 on the course outline, it is not. It's 5 through 100, multiples of 5. Okay, we'll see you in next video.